All right, good morning. So I'm David Leibs from Oracle Labs, and I'll be talking about some stuff that has nothing to do with any Oracle product, present or future. So we're going to start off with some pseudo-neuroscience and metaphor. And the underlying theme is really about our propensity to get stuck in a groove, or I'll even be less polite, get stuck in a rut. And that's really about an idea called path dependence, which is an idea from economics about how you'll start off with some piece of technology and the early decisions you make will be with you forever. Hundreds and hundreds of years later, they will be influencing the decisions that are made. To go further, we're going to then sort of look at how I, as a human being, was wired as a child. And then we're going to dive into one of my favorite topics on Earth, array programming. It's beautiful, and it's something I think it's well worth your time to invest in. And then we're going to look at some futuristic ideas for what kind of interfaces we might put on array programming in the future. So, I am not a real neuroscientist, but I did play one once at NASA in the early 1970s. And what I'm going to talk about isn't real. It's not how we really work, so it's really going to be metaphor. So let's look at what happens when water falls from the sky and hits a little piece of ground. It makes a dent. And that little dent now is a place, the next time the water hits it gets a little bit bigger, and water is very much an optimizer, and before long it turns into a little bit of a groove, and the groove becomes a rut. And over time, water carves amazing deep canyons. So I maintain we're like that too. We're very influenced by what we first learn. And we practice things that we're drawn to. So we lean towards that what we like, and our first experiences have a huge impact on that. So as time goes on, we just get into a groove. So let's play with this idea for a second. This is one of my favorite optical illusions of all time. It's not really an optical illusion, but what do you see? I'll give you a second. All right. Can you see the cow? Anybody? There you go. It's happening. That little drops are hitting. Maybe that little outline around its face will help. If you can't see it, that's okay. See me afterwards and I'll crank it up and we'll give you the experience. Anyway, those of you who were able to see the cow, can you not see the cow? And that's the important part. Once you have seen that cow, you will never be able to not see the cow. And ultimately, we find ourselves at the bottom of canyons, loaded down with all of our stuff, slogging through the water with our friends. We might well find ourselves at the bottom of a for loop. Now, to most programmers, this code for matrix multiply, it looks normal. But to me, I see a canyon. Being dyslexic, rotations don't matter. So it's important to remember to climb out of these canyons that we're in from time to time, even though it's difficult, because there's some things out there that are of just absolutely great beauty. You have to go and look into some of the other canyons that are there. Okay, truth in advertising. Let's look at how I was wired as a child, because this is going to have something to do with where the whole thing goes. I had a very strange toy I played with as a child. I played with clothespins, and I would clip them together into structures, and then I would throw more clothespins into those structures, and I'd try and set off a chain reaction. And it wouldn't happen every time. Sometimes the magic would work, sometimes it wouldn't. It was an obsession. I did it like every day. And at the same time I was doing it, I was sitting on the floor in front of a television set, hooked into sort of the information stream that was just coming in. Sometimes it was interesting, sometimes it wasn't, but I was still there trying to set off those chain reactions. I really, really liked some of the stuff I saw on television, and it's just like, wow, I think I want to be a scientist, right? It's the 1950s, right? Why? Well, because scientists are the ones that get to fight monsters, obviously. I like science fiction. And one day, I had this amazing experience where a real scientist came on TV and started explaining how nuclear chain reactions worked, and explained how one slow-moving neutron would go into a atom of uranium, isotope 235, and it would split, and two more neutrons would come out. This is just what I'd been doing with my clothespins all along, so I really got it. It was an amazing experience to see that which I had been doing sort of connected to something in the real world. Anyway, years go by, and finally, fortunately, I got drawn to mathematics. Anybody recognize that person down in the bottom? Oliver Heaviside. He's a person that was known for coming up with the notation that we use for vector calculus, and it's pretty much, if you do physics, it's your notation. Anyway, so I was clearly neglected. They didn't give me, proper toys to play with and steer me into, more meaningful, directions as a child. But so what happened to me? Well, strangely, I find myself doing today what I did then. I sit in front of a 30-inch monitor, hooked into a stream of information, coming in from the internet all day, and I clip together abstractions and get to a point where I think it's ready, and I'll push the plunger or throw something in and see if that chain reaction sets in and I get the effect I want. Lucky for me, I got to have the good fortune of being the person involved in taking Smalltalk 80 out of Xerox PARC and turning it into a real product. So, just one more data point. Here's my oldest child, what he was doing as a baby, and what he's doing today. You note there's a pattern here. All right, so let's get back to those grooves now that I've told you how I'm wired, and let's look at something really beautiful. Get some water to prepare myself. So, back in the 1950s, at the time I was playing with clothespins, Ken Iverson was playing with notation. He was not satisfied with mathematical notation. He found it filled with inconsistencies, and he came up with a much better notation, and this was at the dawn of the computer age. He wrote a wonderful book. We just celebrated the 50th anniversary of that book, and he was at Harvard at the time he was doing this, and I think sort of lucky for us, he didn't get tenure, and his person he was working with there it's like, well, you haven't really done that much. You only wrote that one little book. But it was quite a book. And so anyway, he went off to IBM, and with Aidan Falkoff, they invented the computer language APL. So sort of a quick overview. It had hieroglyphic symbols. It had its own selectric golf ball where they put their own glyphs on it. It had its own keyboard. He didn't like precedence rules, which are sort of forced on us by algebra teachers so that you don't have to write as much when you talk about polynomials. It appears as though the evaluation is right to left. There's a notion of a workspace, or like if you'd ever done small talk or something like that, it's like you snapshot an environment that's filled with your data and your variables and your code, and when you come back later, you just take up where you left off. And it operated on multidimensional arrays as its main data type. And so its functions are defined on scalars. You have operators that are defined on functions. So operators take functions as arguments and make new functions. And this all then extends to arrays in 4 different ways. Element by element. You can do reductions across arrays of any dimension. And you tend to use inner and outer product as building blocks. And the people that were really drawn to this language were the applied math crowd, economists, chemists, physicists, people that had problems to solve. So they would write code, they would write programs, but it was always in the process of solving a problem. They wanted an answer to a question. They were exploring a space, or maybe they were designing algorithms. So it's like not necessarily the same kind of programming we normally do, but it's in sort of that area of technical computing. So APL has a really, really great idea in that your data is multidimensional, and you can take any multidimensional, be it like a number is 0 dimensions, a list is 1 dimension, a matrix or a plane is 2, and you just extend it all the way up. And you can look at those in multiple ways, kind of like looking at a cow. You can think of it at the bottom, you have 0 cells, which hold scalars, or an atom. And then you can have rows of atoms, or you can look at the frame of it as saying, well, I've got a 3 by 4 frame of rows, or a one list of 3-dimensional arrays. So you can look at it anyway, and because functions themselves have rank, right? The idea of rank permeates APL. You have the ability then to write a function and say, I'm only interested in numbers, or I'm only interested in rows, and then APL will automatically take something of a higher dimension and figure out what to do, call each appropriately sized thing, and assemble the result into a proper frame. And this is what gives you the ability to program without having to write loops. The loops are implicit in how you set your data up and the way you write your functions. So, a little bit of information from the history. APL had reasonably good performance. The first implementation that they did at IBM completely beat the 360 attempts at like time sharing in that, because they paid attention to the movement of the disk head. In other words, the other groups doing things at the time let the disk head jump all over the disk, and the APL guys were careful to do their time sharing by scheduling it based on minimizing the movement of the disk head. So they outperformed it hugely, and it went on to become very, very popular. So here's some performance numbers back from those days in the point in time when IBM was selling APL to everybody all over the world. There'd be a little bit of setup time for an operation, like a couple of milliseconds, and then you were operating on big homogeneous structures, and once you'd gone through that little bit of setup, then it would just crank through the rest of it. So if you had 1,000 elements, the setup time and interpretation was negligible, and the rest of the time was just executing really, really fast machine code. And if you had like less than 1,000 element array, well, it didn't matter. 10 element array, you won't even notice. What's interesting is how well modern implementations perform on an iPhone. It's just totally amazing how fast it is today on little devices. So whatever happened to APL? Well, it grew rapidly in the 1970s, and in the 1980s it started decaying off because PCs were coming on, workstations were coming on, and it sort of died out. We've got modern descendants. It's still used quite a lot in the financial community. It gives them a big edge, and there's people out there writing high-frequency trading systems in APL descendants. It was very influenced Fortran 90, MATLAB, R. It's the ideas in Microsoft Accelerator, Intel's Array Building Blocks, Mathematica. Anyway, so let's look at a little of it. The version of APL that I like, that is my favorite, is a version called J, which is what Ken Iverson did after, I don't know, when he was about 30 years in, he decided to redo the whole thing. He said, we made some problems early on, and I'm just going to start with a clean slate. And he made a version that's ASCII based and doesn't require a fancy, strange keyboard filled with Greek letters. Anyway, here's my 10 by 3 working subset of R, which is mostly just some statistical functions. And the fact that I can put them all on that one grid and get my head around the whole thing at one glance without having to scroll is something I find very appealing. To you, it probably looks like line noise. So anyway, these array languages can be very, very fast. There's lots of experience going back to the 1970s on how to do really, really efficient implementations of array processing by holding off, jumping in and executing code too quickly. In other words, rather than execute, you build a little bit of an abstract syntax tree and look at it a little bit and say, well, gee, they really set up a pipeline here. We know how to do this much faster. We're not going to make a whole bunch of intermediate arrays. There's no reason to do that. So there's a lot of experience in optimizing these languages. In the 1990s, when people started getting more serious about parallelism, they noticed that most of the primitives were just naturally parallel. And because of the way APL works, people would tend to write 40 to 50% of their code would just be naturally parallel. And this is one of the things that I think is what's interesting about why we would want to look at an old language that isn't as mainstream as it once was. It's a good way to train our thinking for doing data parallel computation. So you tend to program by using big building blocks and putting them together with sort of, let's say, higher order functions, and you don't entangle a bunch of information in loops. It's like when we write loops, we have the best of intention, and we try and be efficient, and we try and make them do more things at once, and what we're really doing is getting in the way of the loop fusion machinery. And we're actually much better off not thinking that we know how to optimize code and letting the compiler do it. In other words, much of our intuition is wrong, especially in light of memory hierarchy issues. So APL and its descendants encourage wonderful loopless, thinking, where you tend not to use accumulators and loops. And so here's a really, really beautiful piece of APL, and I'm going to now give you some animations to give you a taste for how to do this sort of thinking, and then we're going to come back to this function once I've introduced a little bit more. So let's start off with just simple arithmetic and adding 3 plus 4. So it'll take the element to the right, the element to the left, and compute. And this animation here is sort of now, I'm starting to show what goes on in my head when I think in terms of array programming, or what I call array thinking. So the sequence of animations is something that I'm kind of designing in hopes of someday having it on some little device like a sunspot with a cheap e-ink LED and some simple near field, maybe some cheap near field Hall effect sensors, so you would know what was to the right and what was to the left, because my dream is to actually pull it off the computer and get back down on the floor like I did with my clothespins. So watch it as it executes this time, and you'll sort of see the right to left evaluation. Computed that. So once you understand adding scalars, well, there's nothing magic. It'll extend in the same way to arrays. And you can mix scalars with arrays. So, all of these functions work the same way, and these are typically the building blocks that you normally use, and everything works the same way. So, next, stylistically, you tend to have interesting functions that can take scalars as arguments and make arrays out of them. So, this is a function called integers. It makes the integers from the first 4 integers, 0 through 4, and it's often just called iota for the character. And you can, of course, give iota an array, and it'll generate for you a multi-dimensional array. So now, what do you do with arrays? Well, you sculpt with them. So here's, let's just generate one and then reshape it into something else. Right, so vector in and matrix out. Now, the real power comes in when functions themselves become data and you have operators, or in like the J dialect, we call functions verbs and we call operators adverbs. And anybody, can we guess what we call the numeric data? Nouns. Okay, so that slash is a adverb that is going to take plus and turn it into, we'll watch it. So you take that and you turn it into big sigma, and we'll sum the whole thing up. Now, my favorite of the operators is prefix scan. So here we've got a chain of operators going. So generate our list, make big sigma. Now we'll apply that to every prefix of the array. And so what we get is a running sum. Now, this can be very useful. So the way you can use this now, it's like we're going to write a function called expand, right? So what we want to do is have an array, and we want to put zeros in all the places, after all the places where there's a 1, and where there's a 0, we're not going to do anything different. So to do that, we'll use that prefix sum, and when you do that on something Boolean, you get a nice walk of the indices, and then I'll multiply it by the Boolean again, right? So do that, and what that does is, it uses 1 as the identity element and preserves those indices, and the zeros annihilate just like you want. So what I wind up with then is this nice thing with the zeros where I want to do my expanding. So here's the same expression together. This is an indexing function, and I'm going to concatenate a 0 onto my array, and when I index into it, out pops my values there with the zeros where I want them. And so that's how you use prefix scan. And prefix scan is very nice because that's something that we know how to do in parallel, and that's built into GPUs. And so if you start getting into GPU programming, you use prefix scans all the time. Okay, the other big function that gets used a lot is outer product. And what that does is it takes every 0 cell on the right and uses the operation that you pass in with the row on the right. So in other words, we'll take one. Well, let's just let it run. It's easier to watch it. There. So we basically we start with one-dimensional things, and we lift the dimensionality to 2 dimensions. And then the other interesting operation is compression. So on the left you have Booleans, and on the right you have some data, and a 1 will select the element and a 0 suppresses it. right? So here's an example. Take the modulus of each number, pick the ones that were equal to 0, resulting in a Boolean, run that through compression, and out pops your data. But compression is really copy. That's why in this, and by the way, the symbols that I'm using, it's my own notation. I'm making it up so we don't get bogged down in a real language. So compression is really copy, because the number that I give it is how many copies of it we want. So 0 is a convenient way of saying I want no copies. All right. Now, we're ready to go back to that example and understand what it does. It's one of the things that I think is one of the prettiest pieces of APL code, and you're prepared to understand it as I walk you through it. What we're going to do is figure out the primes in the numbers up through 15. Just a nice small number. So, okay, we're used to this. Let's generate the first 15 integers. We'll add 1 to each of them. We'll drop the first 1 because 1 isn't interesting to us since we're hunting primes. And I'm going to assign that to a variable r. Now, I apologize for using a variable, but I could do this without the variable, but it would drag in so much more detail. On a first exposure, it's unnecessary. But the good news is it's static single assignment. I'm not going to reassign that variable. Okay, so now that we've got r, that shaded area is something that's like something in parentheses. We're going to evaluate it before we go on, but I sort of like using a highlighter instead of parentheses, and it nests better, and if you have multiple colors, it's easier to see. Okay, so let's evaluate the sub-expression. First off the bat, let's go back to elementary school and build a multiplication table of those first 15 numbers and multiply every one with every other. And so this is the example of upping the dimensionality, a classic technique in array programming. And once we've done that, we're going to flatten it. We'd much rather have it be one-dimensional because we're going to use the membership function, and we're actually going to take our first numbers, 2 through 14, and find the ones that are in that table. Those are the ones we don't want. These are the ones that weren't in there, hence primes. So now all we have to do is go back to our copy machine and select out of our integers the ones we wanted, and we've got our primes. So no loops and a faux variable, and you can see the notation down below that I spared you from. It's really not that bad. And if you don't like Greek, there's the ASCII J, which one can learn to read. Okay. So, remember those grooves? APL and its families are in a groove all of their own. I love it. It's beautiful. If you were to spend the time to let it into your head, you would love it too, and it would show you a wonderful new way to think. But learning it's a little bit prickly, And I promise, though, it will expand your brain. So I've really been setting up all along to talk more about path dependence. And the array programming community and us as well, we're all stuck in the mother of all ruts. The idea that started when they stuck a teletype machine onto a computer, and then later on when they had displays, they emulated the teletype machine, and we do everything through this terrible little one line at a time funnel. Likewise, that little golf ball that was the head that people typed with, that's a really limited number of symbols, and we've got all of Unicode to work with. And to be honest, we don't even have to be stuck with Unicode. We can, we can use candy-colored tiles and jump right to an iPad. And have you ever watched children have their first experience with an iPad and how quickly they take to it and start doing things? Anyway, we could recast array programming to make it easier to learn as a puzzle game. As a matter of fact, the APL and its descendants, J, is really very much a data flow language. Once you know what's really going on, it's strictly data flow. And so this is a little puzzle game I threw together where rather than having it be implicit, you actually see the path of the data as it goes through there. And anything you touch is the immediate evaluation of it and shows you what was to the right and what was to the left and all the ranks and all of that. So, we're going to make it. Okay, so here's, I did a little interaction design the other day. So, suspend disbelief and pretend for a minute that this is an iPad. And we're just going to have 3 blank boxes. So we could grab it with our finger and drag it out. And press on it and open up a nice little wheel of our symbology and pick a function. Drag up a box for a noun, and then, drag off of it, and it'll just let you scroll through numbers. You could use a keyboard, but this misses the point. I want to get away from that path dependence there. Need another. Drag further up, goes faster. And the idea is, what is this read eval print loop business? In other words, it's like, I want continuous evaluation. In other words, we do continuous delivery. We do continuous, merging. Let's do continuous evaluation while we're at it, especially in a language like this. So it's just always evaluating. If I drag the other way, I clearly want to be making a list. So change the function to something else. Done. Just drop an adverb up there. Make space. Big sigma. Okay, so that gives you an idea of the kind of things these languages are 50 years old at this time. We have lots of experience, and I'm really more interested in the next 50 years. It's not going to go away. In other words, 50 years from now, we're still going to be using computers. We're not going to give them up. And what can we do to help relieve some of the path dependence that we're stuck in? So here's a little example of getting off of that one-dimensional narrow little line, that little straw that we type into and do things one line at a time every now and then, using up arrows and down arrows to get the history. It's like, why are we stuck on one line? That was something that was forced on us by a Selectric typewriter. We can go to 2 dimensions into something that's more like a Scrabble world. So this piece of code is interesting. This is a chain of 3 verbs. Well, actually, it's 3 verbs and an adverb. And so this is like arithmetic mean, and we're going to work our way up quickly through some basic statistics. And once again, this is going to focus on the data flow, and it's also going to let you visualize the inherent parallelism. So split, do those 2 and combine, and we're done. And so it's like we can give things meaningful names using that highlighting technique. And so now we're going to just, use the regular deviation. That little hand points over there. It says, give me the argument that was on the right. So I don't have to use a variable. And now we'll just build our way up, and, we'll do the sum of the square deviations. That little circle that was there was composition of function. You'll notice that that's a sequencing operator, and it's also a bottleneck. So, okay, let's do some futuristic ideas. Here's my little friend Karis, and she's playing with my computational blocks that I made out of acrylic. There's no electronics in the blocks. Anyway, she's playing with them, and she's, there she goes. She's just carving a groove. She's totally tactile, acquires most of the information that she's going to get in the pattern of how she's going to interact with the world through these early experiences. And I really like the idea of getting computing off of the computers. And where we're going is really with more and more use of vision. It's like I can go out and I can buy a depth camera from Microsoft for about $125 US, and I can polygonalize reality. I can recognize people by their skeletons, and that is just starting. We've been living with Moore's Law for how long now? Some of you out there, your entire life, you don't know a time that you weren't being subjected to Moore's Law. And we do not have a good intuition for exponentials. And we cannot appreciate what's getting ready to come down in the next 10 years. It's going to be totally amazing. Anyway, with vision, we should just be able to take a picture. And just lift it up into the digital domain, and there it would go. So you can see I'm still doing it. I want to play with those clothespins, right? I want to play with those clothespins and sit in front of a big TV, but I want to do my programming with manipulables and just lift it up. So here's some resources. I guess this will be up on the website. J is a really, really, really interesting array programming language, and it's a good way to train how you think. Ken Iverson's talk for his Turing Award is a must-read. It's notation as a tool of thought. In other words, learn a little bit of array programming first. You don't want that paper to be your first exposure, but maybe your second or third. And it is amazing paper. Another interesting language out there is K and Q, which is created by KX. It's mostly used on Wall Street. The array programming community is small, but they have very, very, very good customers, and they're not a commodity item. They're very, very sought after, and Wall Street will gulp up any competent K programmer. Then, of course, there's the classic itself. My friends at Dialog make a classic, and they're adopting a lot of the really, really good ideas from J slowly. And then, of course, for the people that didn't have time because we went too fast, here's the information for the cow. And that's it. I guess there could be questions.
We have time for like one or two questions.
And is there anything inherently connecting these types of syntaxes with array programming, or could they potentially be mixed into a more conventional syntax as well?
Well, I would say yes. And my favorite array programming language is actually Mathematica. And that that's exactly what they do. It's like, to me, the APL languages, or K or J, have to be a complete language. So at some point they have to adopt the sort of the normal things one needs to do your work. But for me, the real beauty is at the expression level. So I see it as a wonderful sort of domain-specific language, or just ask your language vendor to please give us array extensions, and don't make plus and time so limited. In other words, naturally extend them. I mean, could you imagine how cool a data parallel JavaScript would be? I mean, why not? You know, if the JavaScript is going to rule 50 years from now, let's hope we have a data parallel JavaScript. Yep.
Okay.
I just want to say, please make your slides available.
They are.
They will.
Yeah.
The next question, this one was for free.
And,
so we have one more.
And one more truth in advertising, all of the animation in that was done with Mathematica.
How do you like C# link? What's that response to array programming that expand and
Yeah, that's certainly another way to do it. I like the more compressed notation, but link is recognizable to me. See, it's the kind of thing that once you've learned to think that way in terms of writing your code with powerful functions and using powerful operators to combine them with, and I can't write loops anymore. In other words, it seems like every time I try and write a loop, I just introduce more bugs. Does anybody have that experience? So once you've learned to think that way, you can do it with anything. Last one.
So how would something like J compare to something like SciPy or NumPy?
I don't know. I don't really know SciPy, but they adopt the ideas because you do want to do big wholesale operations on arrays. So at some level, but I find that when you put yourself into the real spirit by using one of those languages, you take some amount of time to sort of break through into to sort of naturally composing that way. In other words, you become fluent in the language, and your mind is forever changed.
All right. Well, let's thank the speaker again for